Welcome back to today's video. In today's video, we're going to discuss training and evaluating the training sets, particularly looking at the entire training set and comparing it to the results of our linear regression model. From there, we'll discuss how we can use the decision tree regressor in order to create a non-linear relationship between our attributes and our output labels. Before today's video, make sure you hit the subscribe button down below and like the video for more content just like this. Let's go right into it. All right, so let's discuss here what we did in the last lesson. So in the last lesson, in the last tutorial, we discussed basically how to create a linear regression model in scikit-learn, as well as how to test the accuracy of a sample size of the population. And so we saw there how we tested the first 5 instances of the data, compared it to the actual values, and compared it to what the values that the model was able to output, and we were able to compare that. And when we did a mean absolute percent error analysis on it, we found that the model had a 35.2% inaccuracy for the first 5 data instances. Now, obviously, this is not representative of the entire sample size. And so because of that, what we're going to do is we're going to analyze in today's video what exactly is the error of the entire population size. So every single data instance within the population size. So in order to do this, we have something called a mean squared error. A mean squared error measures how far predicted values are from actual values by computing the difference of each data point, squaring these differences to remove negative signs, and penalizing large errors, and then averaging those particular errors. Let me go ahead and show you the equation that we use here for the mean square error. For the mean square error, you're seeing this equation here. You see here that you have y sub I minus y sub I hat, and the y sub I hat is the error that the model it's not the model that the error has. It's the value that the model is projecting. So it's the value that the model is projecting. And then we're going to say, what is the actual value that the model is supposed to project? That's what our y sub I is. Okay? And so we're going to figure out the difference. And so let's say the model projects that the median house price is going to be 100,000 and the actual value is 120,000. Well, then we'll subtract those two values and we'll get 20,000, right? And then from there, what we're going to go ahead and do is we're going to square it. And the reason why we square it is because we want to remove the negative symbol. And so if the model, on the other hand, were to say the predicted value were to be 120,000 and the actual value were to be, let's say, a value that would result in a negative value, we want to get rid of that negative value by squaring it. Now, keep in mind that this does penalize larger errors. And so if you were to, for example, have an error of 10, let's say, that would result in you having 100. Whereas if you would have an error of 1, let's say, that would be an error of 1. And the reason for that is because as you square numbers, as you approach positive infinity, when you square those numbers, it results in that number expanding even further. That's exponential growth. Okay, so the rate at which it is increasing is not exactly linear. Okay, it's not linear at all. It's increasing exponentially there. Okay, and so it's going to penalize those bigger errors. And then what we're going to do is once we find all those errors and square them, what we're going to do is we're going to divide them by the number of data instances. So we're going to divide them by the number of data instances in order to get the mean squared error for each particular row on average. So the average mean squared error for the entire data set. And then from there, we obviously want to get rid of the square that we put here. And so we're going to solve the root mean squared error by taking the square root of the mean squared error. And so when we take the square root of that, we're able to bring the values down, the average error rate, into the actual error rate because we squared it when we were doing each of the individual instances. And so this root mean squared error is going to be the actual error. Okay, so let's go ahead and talk about how scikit-learn does this. As you see here, you have the root mean squared error. The root mean squared error represents the typical size of prediction errors in the same units as the original data. And the reason for that is because when we take the square root, it's going to be back to the same units as the original data. Okay, so when we square it and then take the square root again, you'll go back to the units of the original data. Okay, and it does give more weight to larger errors. So when we have a larger error, if you square 10 compared to if you square 2, you're going to see some exponential growth occurring there. All right, so in scikit-learn, we have the mean square error module that we can import from the scikit-learn.metrics. And from there, we can create, we can use the same linear regression object that we created before. So we created a linear regression object before. But what we can do from that is we can say predict, we can call the predict function for the housing prepared, Remember, the housing prepared is all the data instances, the input data instances. So in our case, that would be the attributes. So let me go ahead and show you again. So the data housing underscore prepared, if you remember, those are all the input values. So they're basically all of these individual values besides the median house value, since that's the value that we're projecting. Okay, and we saw that we actually prepared that data a couple of lessons ago. As you can see here, you saw that we have the housing prepared data as such. Okay, so we have that there. And so we're going to pass in the housing prepared data, and the linear regression model is now going to predict what the housing predictions are. Again, using that same model. So this way, we're going to get the mean squared error for the entire data set, not just for 5 of those instances. Okay, so we're going to say mean squared error. We're going to call that function there. And then what we're going to do is we're going to say housing labels. We're going to, sorry, not the function, right? It's actually going to be a object rather, or a class, and we're going to pass it into the constructor. We're going to pass in the housing labels as well as the housing predictions. Remember, the housing labels are the values that we want the model to project, and the housing prediction are the values that the model actually projected. And we're going to calculate a mean squared error comparing each of those data instances using the equation that you just saw right over here. From there, what you'll do is you'll take the square root of that. So you'll use this square root function and take the square root of the linear mean squared error. And then from there, you're going to be able to print out the linear root mean squared error, and that's going to be the error in the original units that you want that the median house value was in. Okay, so let's go ahead and run that there. Let's go ahead and see what we get. So you see that we get 68,866. That means that the model on average was off by roughly around $70,000. Now, in our case, that is not good at all, because when you look at most of our data instances, you can see that the average price of homes hovers around anywhere from $100 all the way up to $300,000. And so having a $60,000, $70,000 error rate on average is not very good. Now, there are several reasons for this. One of the reasons potentially could be that a linear regression model is not good because it doesn't account for varying trends within the data, right? If you're just mapping everything with a line, that might not be particularly useful. And so a decision tree regressor supports nonlinear relationships in our data. And so we're able to create a nonlinear relationship instead of just simply having a straight line. So we have the decision tree regressor. So the decision tree regressor, we're going to create an instance of that particular object, and then we're going to call the fit function. Remember, the fit function learns the data parameters. It doesn't actually apply any of the data parameters, right? Only when we call the predict function, it's going to predict it for these individual use cases. Now, the reason why we're not calling fit underscore transform is because we're not really performing any operation. We're not really performing any operation. We just want to get we just want to we just want to fit the data and see if the model can learn trends in the data. So we're passing your housing prepared data, which, remember, our housing prepared data is our data that is all of our attributes, and our housing labels are all the output data. So remember, it's all of these values right over here. And so what we're passing in is we're passing the true values that the model should be projecting, as well as all the attributes. And so we're going to be passing that in there. And then from there, we're going to calculate a mean squared error. And so, sorry. From there, we're going to go ahead and take the housing predictions, calling the predict function. And so we're going to pass in the attributes, and we want the model to predict what are the outputs. Now remember, we already passed in the outputs when the model was looking at the data. So when the model was not looking at the data, rather, but it was analyzing the data in order to observe correlations. And so we're going to call the predict function in order to predict based on the attributes. And again, this is going to predict the median house price for every single row in the data frame. All right. And so then from there, or not in the data frame, but in the NumPy array, all right, in the dense matrix. Okay, so then from there, we're going to call the mean squared error. So the mean squared error. And the mean squared error, what it does actually is it's going to take in, again, the housing labels, and it's going to take in also the housing predictions. And so remember, the housing predictions are the values that the model was able to produce, taking in those attributes. And the housing labels are the actual values that the model should be outputting in a best case scenario. And so it's going to perform a mean squared error, and we're going to take the square root of that again. And then from there, we're going to go ahead and print out the error rate. Let's go ahead and print out, run that first thing, first cell rather. And let's go ahead and run the second cell. So you see that we got a 0.0 error. Now, that might seem like that's way too optimistic. How can a model have a 0% inaccuracy? Well, the reason for that is because what the model did was is it actually looked at the housing labels and it directly mapped the housing prepared data to our housing labels. We obviously don't want that. We want the model to actually be able to predict the future data rather than simply just memorizing the patterns in the housing labels. And so a better technique for this is to instead, rather than passing in the housing prepared data, which remember the housing prepared data is our training set attributes, we should pass in our test set attributes, and using our test set attributes, we should compare them to what the actual results were in our test set. And so in the next few lessons, we'll discuss how we can do cross validation, by using our test set rather than simply using our training set. Because if we're using the training set to prepare our data, and again, in this case, we're using supervised learning, then if we're just passing in that same data as input, what the model is going to do is it's going to simply memorize those values. All right. And so we're going to talk about how we can do cross validation by using our test set in order to test the model based on instances it has not seen before. And so that's what we're going to be doing in the next lesson. If you like this video, make sure you hit the subscribe button down below and like the video. We discuss how to train and evaluate a training set, how to calculate the mean squared error, as well as how to calculate the root mean squared error, taking a look at how we can use the decision tree regressor in order to create a nonlinear relationship in our data. And in the next lesson, we'll discuss how exactly we can perform cross-validation on our data in order to basically see how accurate our model is on new instances that we have not seen before. I'll see you guys in the next video.